Yep. Before we get started, while we're waiting for other people, sorry. Yes, Caden, to answer your question, today we're pretty much just going through drivetrains, the construction, decision making on that, a little bit of electronic, very, very little, and some programming stuff on specifically drivetrains. Here's the overview of what we're talking about today. Otherwise, if there's any specific questions that people have now on drivetrain stuff that you wanna ask, as we go through our presentation, we may be able to touch on those things a little bit more, just to try to tailor the presentation a little bit more to who's here. If not, if you have questions at the very end, we have some time for questions at the end, and our emails posted as well, if you guys have questions after today that you want to ask us. But otherwise, I think we're good to go. You good, Dilpreet?
Yeah, and Danny, you got it. All right, so I guess we'll go back a slide here.
All right, yeah, if we're all good to go, welcome everyone to the Drivetrains breakout room. Our speakers here are Nick and Dilpreet. Both of them are head mentors from Team 6574 out of Whitewater. Nick is a recent graduate of nuclear engineering at UW-Madison, and Dilpreet is president of the Southeastern Wisconsin Robotics Coalition, and he is studying mechanical engineering and computer science at UWM. With that, I'll have you guys take it away.
Thanks, Michael. So yeah, I'm Nick. I'm Dilpreet. This is Nick. Real quick before we get started, shout out to Ernst and Wes from the Hilltoppers, Team 1732. They did this presentation in previous years and were kind enough to forward what they had worked on and let us use that as a base moving forward. So yeah, they're good guys.
Okay, so today you're learning about drivetrains. So quick agenda of what we're doing. First, a little overview of drivetrains and the importance of them, and then a little bit about wheels, then talk about some drivetrain types, some methods for selecting your own drivetrain, some methods of constructing your drivetrain, motors that are commonly used for drivetrains, power transmission, how you move power from the motor to your wheel, some controls and programming stuff, and then some drivetrain characterization tools that you can use. So first, drivetrain. What is the importance of a drivetrain? It is the most important part of your robot. Without a drivetrain, you can't really go anywhere. So it is what should have primarily the biggest focus in making sure that it is robust and reliable, and that it's going to allow you to score the points with all the rest of the mechanisms that you design. Because without the drivetrain, the rest of them are pretty much useless, with the exception of very few games. I think some years there were games where you could get away without a drivetrain, but that's very, very, very niche. So yeah, So.
And to jump in really quick and really hammer this point home, a lot of top 8 teams will automatically disqualify teams off their pick lists if they have inconsistent driving, because that can be a huge hazard in match play. It's another thing to consider.
Yeah. Okay, so quick overview of the parts of a drivetrain. So first, there is the overall structure of it, the frame and the chassis. So that's what is usually the aluminum parts of your drivetrain.
Sorry.
You're good. I can keep going. So then there's the power, there's the motors. So that's what actually is giving power to your drivetrain to move. There's the powered transmission, which is the gearbox and the belt/chain that is being used to drive the wheels, which is the next part. And then there are the electronics and the code that are on the electronics that allow your drivers to actually move the drivetrain around without pushing it by hand. So first thing simplest thing is wheels. Everyone should know what a wheel is. There are so many different types of wheels out there that we could have a whole presentation on just wheels and why this wheel is better than this wheel for this reason and all these different things. But this is just a quick chart of a few of the different types of wheels that are out there and some of the benefits and negatives for some of them. Really, it's what your team feels comfortable with. I know a lot of teams just use the Andy Mark High Grip, these white ones. Those come in, those are the most basic wheels that I think I've seen teams use as traction wheels. And then there's a few other options as well. And depending on what the game is, sometimes pneumatic is a little nicer. I have a feeling most people have a good idea on wheels. It's just knowing what's out there for wheels. So, going to different places and researching what's around is sometimes a good thing to do. In addition to traction wheels, there are a different type. There are roller wheels. So these ones, in addition to being able to roll in the forward and backward direction, they have extra rollers on them that allow you to move in different directions. So the most basic one are omnis, where the rollers are mounted perpendicular to the wheel's rotation, and that allows the wheel to be able to slide sideways and basically makes it so there's no scrub at all while you're turning. The other ones are mecanums, where the rollers are at 45, and those types of wheels will allow for omnidirectional movement when turned in the proper way. We'll go a little bit more into how that is done when we get to drivetrain types. So I think that's everything for wheels. So drivetrain types, there's a ton of different types of drivetrains. The most common one that you will see from anywhere is a tank drive. Tank drive, it's a very simple drivetrain. You can have anywhere between 4 to 8 wheels commonly. I've seen 10 as well, not as often. And they're all just, one is directly driven from is commonly directly driven from the gearbox, and the rest are powered via belt or chain. There are a ton of different ways to drive it. It is very simple to build, code, and drive. The kit apart drivetrain is just a tank drive, and a lot of the time these can be done in a day, maybe 2 if you're doing completely custom, a week. They're very simple, very easy to do. Most common and successful type of drivetrain, I would say, in the FRC, in general. There are also some things you can do with changing out some of the wheels, so you don't have to use all traction wheels. Some teams will use omni wheels in the corners to reduce some of the turning scrub. Sometimes the middle wheel will be dropped a little bit on where it is on the side of the drivetrain, and that allows for it's called the drop center, and that also allows you to turn a little bit better. So there's a lot of different things you can do with that. The next one is mecanum. So this one you're using those 45 angle wheels. Each wheel needs to have its own gearbox for this type of system, but by turning wheels that are next to each other in opposite directions, you create a screw type of effect, and it allows you to move sideways in addition to moving forwards and backwards and turning. So it allows you to have that omnidirectional movement. It's sorry, 1 second. So it can be a good drivetrain for games that have low defense and you need more precision maneuvering. But it is not, for games that have a lot of defense, it is not always the best choice. Just because you are on rollers, you can be pushed almost anywhere with a mecanum drivetrain. So knowing the game and knowing what, how much defense will be played in that game is very important in making the decision of what type of drivetrain you're looking for. And this one is not great for defense in general. The last one that we're going to mostly touch on today is swerve. So swerve is kind of like the best of both worlds between mecanum and tank drive. It gives you that omnidirectional movement that mecanum gives you, but it also has all of the what are my examples? All the traction and pushing force of a tank drive. The only difficulty is that they are incredibly difficult to build and design and program effectively. They have for a very long time been very difficult and out of reach for many, many teams. Even today, two of the swerve modules on here are commercial off-the-shelf products that you can just buy and use. Even then, they're not always the easiest to use just from a programming standpoint. So many teams will often work with a swerve drive in the off season to develop it and make sure that it works to a reasonable competition standard before they actually use it on their robot. I would highly recommend to never just buy a swerve drive on, you know, the first Monday in January and say we're going for it this year. That's a recipe for disaster for your season, because again, if it doesn't work well, you got a crappy drivetrain, and then know what, everything else you do doesn't matter because you can't go anywhere. So it's very high risk, but it's very high reward in being a good drivetrain.
One other bit real quick along those same lines is one thing we didn't write on here is that the best teams that are using swerve and are making it look effortless also have their drivers practicing for the amount of time that's on the scale of like hundreds of hours. So if you're not a team that can make sure your drivers are getting that time, that's another very important thing to consider.
Yeah, I didn't touch on the complexity of driving them themselves is also up
Yeah,
there.
that one's a very uniquely swerve one in my opinion. But yeah.
Okay, so selecting your drivetrain. So now that you know about all these different drivetrains and what are out there, how do you decide which ones to use? I talked about that a little bit, but there's so many different things to consider. There's like just this list here is a portion of the things that you have to think about when you're designing a drivetrain of what are we going to do. So how do you design that? So one of those methods is called a weighted average table. So this table here, how it is used is you list down all of the criteria that are important to your team in your drivetrain. So here it's agility, strength, speed, programming, drive, terrain, and design. And then you weight each one of those things based on whatever scale you want. The scale here is a 1 through 9. You can also use a 1 through 5, a 1 through 10. Doesn't matter. It's whatever you choose. And then for each of the designs that you are considering, you grade each one of them in, again, whatever scale you want. This one, again, is 1 through 9, or 1, 3, and 9. So for like a tank drive, it has lower agility, so it's 3, but it has high strength, speed, programming, drive, and terrain and design, so it has 9s on everything else. So basically what you do is you take the weight, the score, and you multiply them together, and then you just add everything across all of the categories. And then whichever design has the highest number is what you, based on your weights and what criteria are important to you, that is the design that is most optimal for you to go to. In general, I would say looking at what you are weighting, how you're weighting everything, and what is most important to you while you're doing it, and thinking about what does this number actually mean, not just doing this all, taking a number and being like, okay, this number is the highest, we're going to go with this. Take that number and then go back to your criteria and look at it and say, okay, how did it score this high? Why did tank score 207 and why did mechanisms score 85? What did I weight important enough that allowed these two numbers to happen? So this one is for, all different drivetrains. The next slide, we have another example. This one, we did the weights 1 through 10, and then the scores for each thing were 1 through 5. And instead of instead of different types of drivetrains, we knew this was our exact data from last year for 6574's 2020 robot when we were designing our drivetrain. we knew we wanted to do a tank drive, so that was already decided. But at that point, we were trying to figure out how many wheels, and if we were going to do a drop center, if we were not going to do a drop center. So we went through the same type of table ourselves to figure out what type of drivetrain would be best for us, and we had decided on an 8-wheel with a drop center was going to be the best design for us for that year. In addition, outside of drivetrains, this type of weighted average table can be used for any type of mechanism. So if you have like 2 or 3 different intakes that you're looking at and you're trying to decide between them, a weighted average table is a great way of narrowing down and trying to figure out which design you should go for. Anything to add on weighted average tables, Dilpreet?
In a roundabout way, yes. Because you asked nicely, I am going to point out that if you're ever not sure about your team's ability to consistently build stuff or your relative inexperience, and you're looking at your preseason and trying to figure out, okay, well, we're worried about the drivetrain. We really want to make sure that it's good and we can move on to other parts of our robot. Just get the kit of parts drivetrain. It's a really effective drivetrain. It really does not lose out super hard compared to other tank drives, a custom tank drive. We see teams at Worlds every year having great robots with the kit of parts drivetrain. You can still be creative. You're not just getting everything done for you. So if you're ever not sure, or you're a little risk averse there, just get the kit of parts drivetrain. It'll work 99.9% of the time.
Yeah, and in a second here, I'll be talking about some of the things you can do with a kit of parts drivetrain to make it better. But okay, so frame types. So how do I make my drivetrain? What do I use to do that? So the main 2 that are out there that I've seen teams doing is either a bent sheet metal fabrication or using some form of square or rectangular tube as the basis of your frame. Either way, how you decide what you're doing is entirely based on what resources your team has. Us at 6574, we usually do tubes, but part of that is because we don't have access to machines that can bend sheet at with any consistency and accuracy. But we do have access to some millwork and some lathe work that allows us to more easily use tubes. But if you don't have necessarily that, but you have a good press in your shop, sheet metal work is a great way of making a very strong and sturdy drivetrain. So the most famous, I would say, the most famous and most important within FRC of the bent sheet metal drivetrains is the KitBot. So as an example, it is, but I wanted to take this moment to talk a little bit more about the KitBot and some of the stuff that you can do with it. It is incredibly customizable, even though it is, not necessarily your design. There's still tons of stuff you can do with it to make it your KitBot, not just the KitBot. So as the standard, what it is just a 6-wheel tank drive with a drop center. Nothing too complicated. With the standard kit, you can change the width, you can change the length, you can put a hole in the front of it if you wanted to have a cutout section for intaking. Not very complicated. In addition to that, Andy Mark sells several upgrade kits. So there's one that allows you to turn your KitBot into a Mecanum drive. There's one that allows you to add tank treads to it. There's one that allows you to use pneumatic wheels. In addition to that, some other places also sell upgrades for it. So like the ThriftyBot sells a gearbox set that allows you to go from 2 motors to 3 motors on your drivetrain. And there's also on Chief Delphi, there are threads of hundreds of messages long of people talking about all the different upgrades they do to their kit of parts drivetrain just to make it easier and make it better. So there's still a lot that a team can do with it to make it the best drivetrain for them, without having to completely manufacture and design and everything that you need to for a full drivetrain. Just be a little careful of going too far away from what it is, because I know our team has gotten bitten by that before, of taking a kit of parts drivetrain and changing it a little too much, and it was not a good drivetrain. I was not there at that time, but I've heard plenty of horror stories of that drivetrain.
Rookie team mistakes.
Rookie team mistakes. Yep. So the other, for the tube, I wanted to show you a simple way of doing a tube drivetrain design. So this is called a Versa chassis system. It's all Vex Pro components. So they will sell you the tube pre-drilled, the gearboxes that are designed to attach directly to those tubes. They will give you, you can get bearing blocks, which allow you to perfectly seat the half-inch hex bearings right into them without having to have precision machining on the tubes. There's cams and other methods for putting those bearing blocks in the exact position you need them to ensure that your belts or chains are perfectly tensioned. So if you are looking to do a tube construction, but you don't have, like, if you don't have a mill, if you don't have a CNC machine, these types of frames can be done with simple hand tools. So like just a drill press, and like a hacksaw. They're incredibly easy to use, and that's the whole purpose, is that you should be able to make a West Coast tank drive with nothing but hand tools by using these products. I guess I just used West Coast Drive and I didn't explain what that is. West Coast Drive is, the easiest explanation is one wheel is always directly driven from the gearbox. So no matter what, if something happens to the belts and chains that you're using, you at least have one wheel moving. So you're not going to move as well, but you're moving. And that the wheels are typically cantilevered with them only being supported on one side of the drivetrain. Is there anything else that's characteristic of a West Coast that I missed?
Not particularly. People might have questions about why those wheels are cantilevered, and we can obviously talk about questions again at the end.
Yeah.
But they're cantilevered for ease of maintenance is probably the biggest strength. You know, you can just pull your wheel right off instead of, in the case of something like little design, you know, you've got to take some stuff off. You guys can see that they're surrounded on both sides. Each has their strengths and weaknesses, and I don't think one is inherently always better than the other.
No.
But something to bring up. The West Coast Drive is more of a concept as opposed to a singular product, in case that was a point of confusion for anyone.
Yeah. So it's just an easy way to do it. And then from there, you know, there's all different stuff you can do for custom drives, but, you know, it really depends on your team and how you do things. So yeah, I think that's good on frame types.
All right, so we can move on to one of my favorite things in FRC, talking about motors. So what are motors? They're the thing that actually, you know, converts electromechanical energy into like a physical kinetic motion. So in drivetrains, for tank drives, actually I suppose most drives, there's kind of a meta of which motors are used commonly. Those are listed there. So when you're picking a motor, you got to think about, okay, well, how fast do I want to go? How much power do we want in the drivetrain? Can the motor handle it? How much current does it draw? And then the most important one, I think, for most teams is how are we using the weight that motor provides to make sure that we're getting some value out of that. So these are all just a bunch of those types. So in general, mini sim drivetrains are tried and true. Teams have been using them since pre-2010, I'm pretty sure. Generally 4 or 6 motor configurations, so 2 per side or 3 per side. Pretty robust, like will almost always be something that works for you in pretty much any given FRC game in recent memory. Due to their density, their thermal density, they're also pretty hard to burn out. If you burn out a sim, something has gone horribly, horribly wrong. But thankfully, it's pretty difficult to do it. It deals really well with heat dissipation, so unless you're running it for like an hour straight, you generally don't have to worry too much about heat in a 2.5-minute match. 775 Pro drivetrains, so that's this motor at the very bottom here, much smaller, but a lot more volatile. I like to joke with my students that they're practically explosive. Those we don't see as much anymore, Nick. I don't know if you want to talk more about whenever the last time you or I ever saw one, but they're really lightweight, but unfortunately along with that and how small they are, they burn out much easier without current controlling and voltage ramping. And if you don't know how to do those things, or you don't have a ton of experience, this is kind of similar to the swerve conversation. Don't roll out the gate kickoff day saying this is the first thing you're going to try for the very first time. It's pretty comfortable to spend some time in the off season trying to use that and really just debugging it. And then the final category, brushless ones. These are the newest ones and have generated a ton of hype in the past couple of years. These are more or less the sim ecosystem, but with significantly higher power density. They're a lot lighter. They've got some fun features like an included encoder if that's something that you've struggled with in the past. And they're still pretty new, and cost concerns can really bite deep for some teams when you're looking at buying brushless compared to, say, like the sim mini sim style. But I'm pretty comfortable in saying first is slowly moving towards these being standard. And so there wouldn't be a terrible thing to, if you have the resources, to buy into and use. We've used both now at 6574. Nick, I think I can comfortably say we vouch for both types. They're both really effective.
Yeah. At this point, yes.
So moving on, how do you actually control your motor controller, your motors? So with a motor controller, you have to be careful, make sure that you don't buy a certain type of motor that's not compatible with an affiliate motor controller. So generally on your power distribution panel, we maybe should have had some images of that, but that's okay. You want to wire these to your higher amperage slots. You want to make sure that you're not putting it on like a 10 amp breaker, because you're just going to trip the breaker anytime your robot starts pushing something. And that's bad, because that'll cut off power for a limited time to your drivetrain, and now you're not able to move. And as we've talked about, that is paramount. You have various communication options. So this will be something more that your programmers can explain, and we won't go super deep into during this presentation. But you can use CAN, which is a daisy chain network between all of your motor controllers and some various bits and pieces on your electrical system, which is really nice because now they can all talk to each other. Now there's a unified communication network. It's what cars use to some degree. The unfortunate side is that this creates a single point of failure because they're all daisy chained. There are some ways to get around that. But again, that's not in the scope of this presentation, but it's not a unilateral weakness. But if you daisy chain them like we do, if one goes out, everything down the chain goes out, and that can be problematic because that might mean you stop moving. Whereas PWM just requires single cables to each controller. It's really simple, conceptually simple, no longer has that single point of failure generally, but it can be really messy. And, just be visually tough to parse. So you can see in each of those categories, certain motor controllers can do more than just PWM can. The Spark Maxes can run over USB. Although I don't think that's, correct me if I'm wrong, the common on the robot itself. That's more of like a testing the controller.
Yes, I believe so.
Okay, but you'll notice that the Spark, which is PWM only, that can't do closed loop functions besides having a forward reverse limit switch, whereas a lot of the CAN controllers have more advanced features that you can take use of. So that's another thing. So like positional feedback, PID control, a lot of that stuff you can only do on most of the CAN supported motor controllers. So at the very bottom, you'll see that instead of a motor controller, we've just got a motor. That's because the Talon FX is just the motor with the controller integrated in. That's part of what makes it so appealing in certain ways, because now you don't have to have more wires. So that is probably one of the bigger considerations, I would say, when you're looking at the Falcon versus the Neo. And to run the brushless Neo motors, you have to buy the Spark Max. So none of the rest of these will work, including that Spark at the top.
In general, brush motors can run off of almost anything. Brushless motors need specific controllers.
Great. So now that we've talked about how to get your motor spinning, we're going to talk a little bit about what that actually like how do you use that? For drivetrains, we're going to talk first about commercial off-the-shelf gearboxes, and then we'll do some talk about some custom ones. Commercial off-the-shelf, you buy it, you put it together, put it on your robot, you're done. Super simple, and I would say if you're comfortable building your own custom drivetrain, but maybe not as much about the gearbox design, you don't want to make something that's unreliable, this is a great way to go. And pretty much all the gearboxes pictured here and more are reliable, work really well, have good examples of teams using them to good effect. I believe the kitbot uses the tough box at the bottom, Nick.
Yes. Yep. The bottom left is what's on the
And
Get Apart
that,
drivetrain.
I think that's just like 3 or 4 gears in a simple plastic housing.
Yep.
So it's really effective and doesn't need to be anything too much more complex than that. But they also have customization options frequently. So like if you wanted to have pneumatic shifting or a power takeoff where you can actually separate the output shaft of your gearbox to power something else in your robot, also controlled pneumatically. Different gear ratio options. A lot of these manufacturers know that one size doesn't fit all when it comes to selling a gearbox. And so they're usually pretty good about including various options for you to customize. So kind of like the kitbot, you still have some options. You're not going to get deadlocked into one configuration for the rest of the year or the rest of your time using that gearbox. And then kind of leading into that, these are generally pretty robust and reliable. So you can reuse these year to year. I think our 2019 drivetrain gearboxes ran for well over 100 matches and we never had a failure.
Yeah.
So I can speak personally to that. But beyond the options they give you, you generally can't optimize much further. And if you have adequate machining resources, cost-wise, becomes a factor that you need to consider for or against.
One thing, can I add to this?
Go right ahead.
Because they are COTS, if you are a low resource team, some of these gearboxes can be expensive. Because they're COTS, you can reuse them the next year. You can use them, if you don't, make any drastic changes yourself, you can just reuse that gearbox. It's completely legal to do so. So that is another one of the benefits of the COTS gearboxes.
So the next, I guess, type, if you will, of a drivetrain gearbox, again, kind of geared towards tank, is making your own custom one. So this can be really nice, especially if you've got all the resources and the know-how, because you can customize to an exact speed. You can decide whether you want it to be a shifter or a single speed gearbox. You can customize the form factor. One of the weaknesses we didn't touch on with the COTS one is geometrically, you're kind of stuck with how that gearbox is shaped, and you got to make sure that works with your robot. You can integrate special features as you want to, and generally, just like with a lot of things, buying the parts and doing it yourself can be cheaper than a COTS gearbox because you're, cutting out the middleman there. With all that being said, these sound really good, and I think us at 6574 are always thinking, hey, should we do this? Unless you already know what you're doing and you've already made these, like many other things in the presentation, don't do it during the build season. Try it in the off season, get some experience with it. And it's a really good point that I think Nick put in there. There's so many COTS options. Do you really think you can do better than them? If yes, great, go for it, because it's a really good learning experience and can have some pretty good benefits for your robot. But again, you really want to make sure your drivetrain is robust, reliable. We're going to keep hammering that point home because of how important it is and how frequently we've all seen teams that have struggled to move on the field, and that can be very frustrating. Anything to add, Nick?
I don't think so.
I think we're doing pretty okay on time. So then another consideration, again, generally for tank drivetrains, is are you using belts versus chains? So a disclaimer, my opinion is that just do whichever your team prefers and works well. There are separate cases where each of these are good on an FRC robot. It's not one size fit all. But for belts, you got to buy them to size. You can, but it can be very difficult to make a custom belt for a custom size. So you have to, take a look at where your wheels are, what kind of pulleys you have. the spacing you require, and then make sure the belts you buy actually fit that. Otherwise, you have to get into the wonderful world of very cramped tensioning space, and that can be difficult. I can link it. We're sharing the presentation later on, so I can link it in this slide. But there's actually a really nice paper done by Team 234 a while back now, but it still holds up, where they actually tested both of these. So I'll try to get through the rest of this and refer you guys to that pretty quick. The big thing with belts and drivetrains, they'll work, they're fine, but you really need to be smart with the size of belt you use. I've seen and have heard lots of issues with improperly chosen belts because if they're too thin or the pitch isn't that great. I've heard of teams like shredding the teeth or snapping a belt, and that means now you've got problems moving. As a general rule, though, we've used belts before. We had a good time with it. They were very similar to the Kit Parts drivetrain belts. That's actually a really good example of a reliable belt-driven system, so you can use that as an example. Moving on to chain gets a little more forgiving. You've got customizable sizes based on pitch, so like a 25 series chain, the distance between the links is just 1/4 of an inch, so really easy to design for, really simplistic. You have a bunch of options. Generally can handle, like, pound for pound, can handle higher stresses and mechanical difficulty than belts do. And then kind of in line with that size conversation, it's a lot more forgiving design and tolerance wise, much more adjustable in the design than belts can be. And the thing I really like about it most is once you get it right, once your center distances are fine, you've got the right chain and you've tensioned it if you need to, you can almost always just set it and forget it when it comes to drivetrains. And due to that reason, it's somewhat in the meta in FRC for tank drivetrains, for the West Coast style drivetrain we were talking about earlier. So personally, at Ferrodermis, this is what we use most of the time, chain. But not really drivetrain related. There are lots of cases on FRC robots where belts are probably a better way to go. Intakes come to mind. I'm sure you guys can think of other examples as well. All right, so now we're getting into...
Jump in real quick. You guys have about 12 minutes until the break room closes.
Awesome, okay. That should be enough. We'll go into controls. This is both like mechanical controls and how you're actually controlling the robot with your controller. So here we've got pictured some pretty basic control schemes. I'm not going to go through each of them, but there's a number of ways for you to control your robot, whether it's with a game controller or not. But the big takeaway you need to have here is that it's super important and your driver needs to be comfortable and able to take advantage of being able to reliably control it. If you can't drive it, you might as well not be able to move too. So that making sure that your drivers have comfortable button layouts and things like that is really important. And that can just be, hey, asking them, what do you think? What makes sense? Sometimes it doesn't make sense, but if they can drive it well, great. I'm not going to ask questions. Last year, our driver decided that he wanted to drive backwards most of the time, and that worked better for him. So that's pretty much that. Make sure that your driver likes what they're driving. And then kind of more along the software control side of it, there's a bunch of things you can do. I'll kind of go through these quick because you can generally just Google all of these, but also we can talk more about them in the questions section or email me later. But voltage ramping, which is controlling the rate of acceleration of your motors, cubing your joystick inputs, brake versus coast mode. I'm actually going to talk about that one a little bit more. So in most motor controllers, you can set it to a brake mode versus a coast mode. And what that means is once you stop sending, like, hey, turn the motor commands to your motors in your drivetrain, in brake mode, it'll stop the motor immediately. Whereas in coast mode, it'll just let it kind of roll and let the inertia of the system kind of carry through. On drivetrains, I'm going to say most of the time you want these in brake, because if you're in coast and you let go of the controls and your robot just kind of keeps going, that usually isn't a good thing. But there are mechanisms where you want coast on your robot. Then there's also deadband adjustments. So that's like adjusting the controller sensitivity, if you will, making sure that like when it's not just set to 0, like it's not just moving the robot by itself. Current limiting. And then the last one, which I think a lot of teams forget about, actually using some of the feedback controls on your controllers. So, most game controllers have a motor on the inside that actually shakes the controller. And you can put that in your drivetrain code to kind of signify like, hey, the robot's reporting this action. So things that come to mind are having your driver's controller, once your robot's ready to shoot, having it shake in your hands, and that way they know, okay, someone can actually tell a robot to shoot something or do whatever task. All right, and the last big thing we have is drivetrain characterization. So we're going to go over two characters, JVN and iLight. These are really good sources of sanity checking what your gearboxes and your drivetrain need, and what the effect of different gearing options and types of motors and quantity of motors, wheel diameter. You can see all that on there. Nick, I don't know if there's anything JVN specific you want to cover.
In the JVN calculator, they also have stuff for some of the COTS gearboxes that are pre-built in. I think most of the VEX ones are pre-built in there. But otherwise, it's just a good tool for, I'd say, mostly figuring out generally what speed you're going to be moving at. Gives you, I think, a good general idea of what you're going to be expecting from your drivetrain.
Mm-hmm. This next one is the iLight drivetrain calculator. This one is a lot more complex in that you have to put more details in, but you'll get more details out. So we actually, I think is this ours, Nick, from last year?
Yep, this is ours from last year.
This is what we did for ours. It's how we, figured out the exact gear ratio we wanted, and then looked at a bunch of these characteristics. And this is not something that you have to do on your drivetrain. Like, you don't have to generate this and then use this calculator to figure all this out. A lot of the times, like I mentioned before, you can set it, forget it, and just move on if you're using something COTS. But if you're looking to get like some extra performance enhancements, you can use this to kind of vet those and make sure you're not doing something crazy, like your robot doesn't actually ever accelerate to its max speed over the distance of a field. Is one, I think, really good bit of information that this gives out. And then go ahead, Nick.
Yeah, so today we only really talked about 3 different drivetrains. There are so many different drivetrains that are out there. So we just wanted to list some of the other, I would say, non-traditional drivetrains that exist. We are not encouraging any of these drivetrains. I think most of them are, a few of these have gotten just outside of the meta. They're just so old. They were used 10, 15 years ago. Some of them are still used a little bit more commonly recently, but for the most part, they're a little strange. And if you think that they are really, really the best drivetrain for you, perhaps it is an option, but for the most part, I usually say tank is the way to go.
And again, if you're ever not sure, go with the kit of parts. Can't go wrong.
Yeah. So questions. I see one from Danny. What's the difference between crab and swerve? So a crab drive is a more basic swerve drive where instead of each motor being, or each wheel being turned independently, all the wheels will turn at the same angle together. So you get a lot less complexity out of the design, but you use fewer motors. They usually end up looking like a big mess of chain though, because you have one motor and one that's chained to all the rest of them. So it takes up a lot of space to do that type of drivetrain. So it's kind of just, for the most part, fallen out of favor in FRC. I think there's still like virtual crab drives where some teams will use their swerve and just program it so all the wheels are turning at the same angle. So it's more of a programmatic crab drive than a swerve drive.
Yeah, Warrior Bots Chris, did we end up covering your question? The question was, what are weight considerations?
Oh, actually, you didn't. It was kind of a. I thought when you were talking about waiting, you were waiting on your selection or criteria. So, for me, is there any consideration with the different weights of the drivetrains, and that might play into why you might go with a tank versus a swerve versus something else to try to maybe save some weight?
Oh, weight consider. Okay. Um, I think in general, I think types of drivetrains are less the consideration with weight than it is type of construction that you're looking for, I think. Um, I mean, certain ones use certain motors. So like when you have a swerve drive, you're dedicated to 8 motors, which is heavier than using 4 for a tank drive. Um, but a lot of the structure that you have in a tank drive isn't necessarily there for a swerve drive, because you don't have, belts or chains going across the entire length of it. So I think it really is more of a detail thing of getting them to making them more lightweight across all of them. I don't think there's really any big difference between the few that we talked about today.
Yeah, I think there are going to be teams that have really well done swerve drives that are lighter than other teams' tank drives, and vice versa. A lot of that weight consideration comes down into like what points in your robot need to be strong in your drivetrain and what material selection you can use. So I would say that is a bigger factor than the exact type of drivetrain.
Question from Caden: what are motors you would personally choose for a drivetrain for a 6-wheel tank? Currently, Falcon 500s are, I think, the most powerful motor that you can use, but it entirely depends on your resources and how comfortable your team is in using those motors. They are $140 per motor, so they are expensive compared to a sim motor where you could use a sim and a simple spark, and that will cost, I think, $60, $65 per motor that you are using with the motor and the motor controller. So it's really up to resources of what you would do. But personally, we use the Falcon 500s because of the power, and we have the resources to be able to do so. The Neos are also very, they're a little bit less powerful than the Falcons, but they're also still a very good option,
Yeah, I would
depending
say
on the system you like to use.
between the Neos and the Falcons, I think at this stage, it mostly just comes down to what you prefer.
Yeah.
Looks
I think
like
we have
about
time for
just a minute, so maybe one quick question, and then we can probably have to be done.
Yeah. And while people are typing, if you have any more questions, email us. We will answer your questions.
Yeah, even if it's stuff we didn't cover, there's a lot of things like material thicknesses and things we didn't cover because time.
Yeah. If there are no other questions, thank you guys for coming. We didn't talk about a lot of the electronic stuff. I do want to plug the presentation after us. Allison Conrad is going to be doing a presentation on the electronics of everything. It's going to be a great presentation. It's in this same room, so please go attend that. It's going to be a good presentation, I think. And thank you everyone for coming today.